do some of the problems from the review worksheet, basically in case you were absent, or just in case you felt like doing it in your groups was not as easy as you'd hoped and you sort of wanted to see how it's done. So let's go through some of the harder problems. The first one says, prove the following identity. Sine 3x is equal to blah, blah, blah. I guess if you'd like, this could be called like a triple angle identity, right? I give you a hint. I say to write 3x is equal to x plus 2x. Now, why would you do that? So sine of 3x can be written as sine of x plus 2x. Why is that good? Well, because what you now have is the sine of one angle plus another, and we have a formula for that, right? What's the formula for the sine of one angle plus another? Well, that's this thing right here, right? That's the angle sum identity for the sine function, right? Basically, what we have is our a is x and our b is 2x. So let's apply that formula to this expression. We get sine of the first thing times cosine of the second thing plus cosine of the first thing times sine of the second thing. Okay, so that is me just applying the sine angle sum formula to this expression. Now this is cool because what we now have is cosine 2x and sine 2x, and we have formulas for those things, right? So it's a little tricky because I sort of want you to specifically sort of like change. I want you to show that sine 3x is equal to this specific expression right here. And the thing is, with cosine 2x, there's 3 different formulas for it, right? So right here you got cosine 2 theta is cosine squared minus sine squared. Hold on. That's one formula for it, but there's also 1 minus 2 sine squared, 2 cosine squared minus 1. Which one should we use? What I would point out is that the right-hand side, the thing that we're trying to transform our expression into, only involves sine, right? Do we see that? It only involves sine. So maybe it's a good idea, I'm not 100% sure off the top of my head, but maybe it's a good idea to replace cosine 2x with the version which only involves sine. That would be 1 minus 2 sine squared x. It's a reasonable thing to try, so let's try that. So this is sine of x times 1 minus 2 sine squared x. Okay, and then we have plus cosine x, and then we have sine 2x. Well, we've got a formula for that too, right? That's the double angle formula for sine. There it is. So we'll go ahead and replace sine 2x with that expression, 2 sine x cosine x. All right. I'm being a little bit inconsistent about whether I put my x's in parentheses or not. I should try to be consistent. Okay, so well, looking at this expression, you know, I think we can clean things up. Maybe the sine x can be distributed to these two things here. You know, I don't know. Maybe that's the way to go. So I'll distribute that sine x. So sine x times 1 is sine x minus 2, and then sine x times 2 sine squared x would be 2 sine to the third x, right? Plus, and then in this expression, what we have is cosine x times cosine x. Those two can be put together to give you cosine squared x. So this whole term is really just 2 sine x cosine squared x, right? Okay. Now, as I said, the expression that we're trying to turn this thing into only involves sine, right? And our expression right now still involves a cosine. So we've got this cosine squared, and wouldn't it be nice if there were a way to replace the cosine squared with something only involving sine? Well, of course there is, right? We can replace the cosine squared with 1 minus sine squared. So that's what I'll do. So I have sine of x minus 2 sine to the third x plus 2 sine of x times 1 minus sine squared x. Okay? So this expression, at least, only involves sine, and the question now is basically, is that the same thing as this, right? Maybe. We sort of have to clean it up and collect like terms to see. One thing you'll probably notice is that the 2 sine of x can be distributed to each of these 2 terms here. Let's go ahead and do that. So I'm not changing this term, I'm not changing the 2 sine to the 3rd x, and I'm just going to distribute this guy here to these 2 terms. So that's 2 sine x minus 2 sine to the 3rd x. All right, well, we've actually got some like terms here, right? We've got 1 copy of sine x plus 2 copies of sine x. That would be 3 copies of sine x, right? And then we've got negative 2 copies of sine to the 3rd x and another negative 2 copies of sine to the 3rd x. That would be, in total, negative 4 copies of sine to the 3rd x. And I think that's what the right-hand side is, isn't it? 3 sine x minus 4 sine to the 3rd. Yep, that's exactly it. Okay, so that's how that one goes. Okay, so let's move on to C. Let's have a look at C. C says that sine of 4x is equal to all of this stuff here, and I give you a hint. I say use a double angle formula. So the idea here is that sine of 4x, well, 4x can be written as 2 times something, right? It can be written as 2 times 2x. Now remember, we've got a formula for sine of 2 times anything, right? In general, we know that sine of 2 theta, this is the double angle formula for sine. Sine of 2 theta is 2 sine theta cosine theta. Well, hopefully you can see that I can apply this formula to this expression here with my theta being equal to 2x. And that's essentially what we have here, right? Sine of 2 times something. The something in this case is 2x. So what that will give me is 2 sine of, well, what is theta in this case? It's 2x. So that's 2 sine 2x times cosine of 2x. Okay. Now, of course, this thing right here is not the right-hand side of the identity that I'm trying to prove, right? Right now, this thing looks nothing like this expression here. But that's okay, because there's a lot more that I can do. The main thing that I can do is I can recognize that I still have some double angles in here, right? I have 2 sine 2x, and I have cosine 2x, and I have formulas for those things, right? So what I'll do is I'll use the double angle formula for sine here, and I'll use one of the double angle formulas for cosine right here. I don't really know which one I'm going to use just yet, but let's see. So this is equal to 2, okay, so it's 2 and then times sine 2x. Well, what's sine 2x? It's 2 sine x cosine x. That's the double angle formula for sine again, right? And then as far as cosine 2x, unfortunately, you know, there are 3 different cosine double angle formulas, right? They're all listed on the sheet right here. As far as which one I should use, it's not completely obvious. But looking at what I'm trying to arrive at, I do notice that there are like sines and cosines floating throughout. Maybe I'll just try the first one. Maybe I'll just try replacing cosine 2x with this first formula, cosine squared minus sine squared, and just see what happens. And if I don't get the identity that I want, then maybe I'll go back and try one of the other cosine double angle formulas. We'll just see what happens. So, all right, so I'm going to replace cosine 2x with, what is it? It's cosine squared x minus sine squared x, right? Okay, notice I put parentheses around there because, you know, there are 2 terms. This whole object is cosine 2x, and this expression needs to be multiplying cosine 2x, which means it needs to be multiplying both terms, hence the parentheses. So, you know, I mean, I guess that comparing this expression with the identity we're trying to achieve, you know, you might notice that the difference between them, maybe I should try distributing all of this stuff, and then maybe it will turn into this. It does look like everything is distributed in this identity. So let's try distributing this expression here to the 2 terms and see what we get. Obviously, this is just 4 sine x cosine x, right? So let's do this. 4 sine x cosine x times cosine squared x is going to be what? It's going to be 4. How many copies of sine do I have? Just the 1. But then because I have cosine x times cosine squared x, that's going to be cosine to the 3rd x. And then distributing this term to the second guy, well, it's going to be minus because of this minus. So minus, let's see, it's basically 4 sine x cosine x times sine squared x. So that's 4 sine to the 3rd x. Sine to the 3rd because I've got sine x here times sine squared is going to be sine to the 3rd. And then just the 1 cosine x. That is exactly the identity that I had on the right-hand side, right? So does that? Yeah, that's it. That's it. Okay, cool. So that's that identity right there. So fundamentally what this was about was sort of using the double angle formula twice, right? You can write sine 4x as sine 2 times 2x, and then repeatedly use the double angle identities. I hope it's clear that, this would kind of generalize, right? Like if you really wanted, it would take a lot of time, but you could come up with a formula for sine of 8x, right? Because you could say, oh, well, that's sine of 2 times 4x, right? And then you could use the double angle formula for sine and say, oh, that's sine 2 sine of 4x times cosine of 4x, right? And sine 4x is something that we just computed. It's this whole thing. So you could replace this guy with this. But then you'd also want a formula for cosine 4x. And you could replace both of them and sort of keep breaking it down until you've just got sines and cosines. So I hope it's clear that you can kind of use these identities again and again to build more and more formulas, which is pretty interesting. All right, let's move on to D. I think D is maybe pretty similar to C. Instead of 4x, it's x over 4. The idea overall is pretty similar. So here's what we're going to do. So sine of x over 4. I give you a hint about this one. I tell you to use, or actually no, I don't give you a hint. I don't give you a hint at all. But hopefully what you can notice is that this is actually half of something. X over 4 can be written as sine of 1/2 x over 2, right? And we have a formula for that. We have a formula for sine of 1/2 something, right? That's the half angle formula for sine. So what is the half angle formula for sine? It's right here, right? Maybe to avoid confusion, I'll call the variable theta in this equation. So in general, the half angle formula for sine says sine of 1/2 theta is, what is it? It's plus or minus square root of 1 minus cosine theta over 2. So 1 minus cosine theta over 2. So that, in general, is the half angle formula. And comparing this expression with this one, we can see that that's exactly what we have, except theta is what? Well, theta is x over 2, right? So so if I replace theta with x over 2 in this formula, I can apply that formula to this. So I have sine, let's see, plus or minus root 1 minus cosine of theta, and theta in this case is x over 2. So that's cosine of x over 2, all over 2. Okay. In a way, we've kind of like reduced the problem, right? Initially, we had like a quarter angle, like x over 4, and now we only have a half angle, x over 2. I hope that it's clear that you can now apply another half angle formula, the half angle formula for cosine, and replace this expression with like another formula, and then we'll get rid of the half angle, and we'll just have an x instead of x over 2. So let's keep going. Let's now replace. So what I'm going to do is I'm going to replace cosine of x over 2 with the formula for cosine of x over 2, which is here. Cosine x over 2 is plus or minus root 1 plus cosine x over 2. Okay. So what do I have in total? I have plus or minus root all this over 2, and then 1 minus, And now I'm replacing this cosine x over 2 with its formula, right, which is this thing right here. So I'm going to get another plus or minus, and another root, and what is it? It's 1 plus cosine x over 2, right? So 1 plus cosine x over 2. Okay, and you know, I've gotten rid of the half angle and the quarter angle, and if you notice, this whole expression looks really similar to the one that I'm trying to prove, right? As a matter of fact, it's basically identical. I think it's basically done. The only thing that you might notice is that I've kind of got this funny expression, 1 minus, plus or minus root blah, blah, blah. Whereas here on the identity, it says just 1 plus or minus. Like there's not this additional minus sign. If you think about it, the minus sign is actually unnecessary. Because what this is really standing for is two different formulas. One plus, right? There's a plus and a minus here. And if you think about it, like if you consider what the plus or minus really means, you have one formula that's 1 minus positive root blah, 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 and another formula which is 1 minus negative root blah, blah, blah. Well, that simplifies to just 1 plus or minus root 1 plus cosine x over 2 all over 2. Like that's the same thing. I mean, you know, what I'm saying here is this expression, the 1 minus plus or minus, you don't need the minus here. Like 1 minus positive 1 plus cosine x over 2 is really just 1 minus root 1 plus cosine x over 2, and 1 minus negative root 1 plus cosine x over 2 is really just, well, because of the minus negative, it's really just 1 plus cosine x over 2. So you can see that this whole expression, 1 minus plus or minus, is the same thing as just 1 plus or 1 minus, right? This minus is not really necessary. That's the point that I'm making here. And that's the answer that I'm looking for. Okay, so that's cool. Let's move on to maybe some of the more conventional problems, right? So there are some sort of conventional problems in here, and maybe I won't do all of them out, but I'll at least sort of tell you, you know, how to get started on some of them. Some of them I'll actually do completely because they are a little tricky. So this is the back side of the review page. So find the exact value of each expression. So we've got sine of 75 degrees. Okay. Well, you know, 75 degrees is not on the unit circle, but certainly it can be written as the sum of two angles which are on the unit circle, right? We can write that as 45 degrees plus 30 degrees. And then we can use the sine angle sum formula, right, for this one. So, you know, it's like your A is 45 and B is 30. So you would then apply the formula. It would be, I always forget this formula. It's very difficult for me to remember it. Yeah, it's sine of 45 times cosine of 30 plus cosine 45 times sine of 30. And what you'll do is you'll replace, you know, you can evaluate each one of these, right? Sine 45, that's root 2 over 2. Cosine 30, that's root 3 over 2, etc. You make all those replacements and simplify. You'll get the answer at the end of the worksheet, okay? B, cosine of 5 pi over 12. You know, it's a bit harder to picture because 5 pi over 12 is in radians. You could actually do this in two different ways. You could do this as a half angle. Like you could say, oh, you know, this is cosine of 1/2 pi over 6, or 5 pi over 6 rather, right? 5 pi over 6 is a unit circle value, so you could then use the cosine half angle formula, right, where x is 5 pi over 6, and do it that way. I think also, though, 5 pi over 6 can actually be written as a sum of two different angles. It's not so obvious how to do that when it's in radians. If you like, you can convert 5 pi over 12 to degrees. So multiply by 180 over pi. The pi's cancel. Between the 12 and the 180, there's a common factor of 6. So 6 goes into 12 twice. 6 goes into 180 30 times. All that's left here, oh, and then actually I can go a little further. This 2 now goes into the 30 15 times, right? So all that's left is the 5 and the 15. So 5 times 15 is 75 degrees. Oh, well that surely is 45 plus 30. So we could rewrite this as 45 plus 30, just like we did for the sine, and then using angle sum formula. So 2 ways of doing that problem. Okay, let's think about tangent pi over 12. Okay, so tangent pi over 12, I would again sort of say that there are 2 ways of doing this. You could say, oh, you know, that's 1/2 pi over 6. And then pi over 6 is a unit circle value, so you could then use the half angle formula for tangent. Or if you convert this to degrees, I'm pretty sure you'll find that it's actually just 15 degrees. And you could say, oh, tan 15 is actually, you can write that as a difference, right? You could be like, oh, that's 45 degrees minus 30, right? And that would also work. I'm going to do it this way, I think. So let's write this as tan 45 degrees minus 30, right? This is going to be a tough one, basically because the simplification is kind of brutal. So the tangent difference formula tells us that this is tan 45 minus tan 30 over 1 plus tan 45 times tan 30, right? So we have to evaluate all of these. Tan 45 is 1, minus tan 30 is, let me see, I can never remember whether it's root 3 or root 3 over 3. All I know is that between 30 and 60 degrees, one of them has a tangent of root 3, and the other one has a tangent of root 3 over 3, and I can just never really remember which one is which. But thinking about whether the tangent would be bigger or smaller at 30 or 60, remember that tangent is defined to be y over x. At this coordinate right here, the y-coordinate is small and the x-coordinate is big. That means that y over x, the ratio, which is what tangent is, will be small here. On the other hand, at 60 degrees, the y-coordinate is big, the x-coordinate is small. That would make tangent large. So the larger of these 2 numbers goes to 60 degrees, and the smaller of those 2 numbers goes to 30 degrees. Which one is smaller? Well, surely root 3 over 3 is smaller. So that's got to be the one associated with 30 degrees. So that's the tangent of 30 degrees. It's root 3 over 3. There we are. And then 1 plus, this is tan 45, which is just 1, times tan 30, which we just said is root 3 over 3. So that's basically it, except it has to be simplified. And simplifying this expression is kind of a nightmare. We did one like this in class, but first of all, notice that I can just ignore the 1 times, right? That 1 is not really doing anything. For one thing, we've got fractions within fractions, and I should fix that. So the numerator can be written as, I'm going to combine these 2. This 1 is like a 3 over 3. So 3 over 3 minus root 3 over 3 is going to be 3 minus root 3 over 3. God, there's a lot of 3's. And then similarly down here, you can view this 1 as 3 over 3. So 3 over 3 plus root 3 over 3 is going to be 3 plus root 3 all over 3. And then we can keep it, change it, flip it. We get 3 minus root 3 over 3 times 3 over 3 plus root 3. These 2 3's cancel, and that's great, but then you're left with this 3 minus root 3 over 3 plus root 3. How do you rationalize that denominator? If you remember, you have to multiply top and bottom by the conjugate. That's multiplying top and bottom by the conjugate of the denominator, I mean. So multiply top and bottom by 3 minus root 3, and that will get rid of the roots in the denominator. So in the numerator, if you FOIL everything out, 3 times 3 is 9, and blah, blah, blah. If you FOIL everything out and collect like terms, you'll sort of get this plus 3. And then here, this is a difference of 2. It's a product of a sum and a difference, so it's going to multiply out as a difference of 2 squares. In other words, this thing squared minus that thing squared. In other words, 9 minus 3. So that is going to be, well, this and this can be combined, right? That's just 12. So 12 minus 6 root 3 over
and then 9 minus 3 is just 6. And then if you like, you can factor out a 6 from the numerator and write this as 6 times 2 minus root 3 over 6, and then the 6's will cancel, and you get 2 minus root 3, and that's the answer. Okay. I mean, what's funny is that what makes this problem hard really is remembering the value of tangent, right, at 30 degrees, and then also being able to simplify this expression algebraically. It's not exactly much to do with the new material, but it is a good problem because it's kind of a review of several other techniques. Okay, I'll do one more of these, or maybe just a couple more. Problems E, F, and G are all like trig identities in disguise. Like if you look at 2 sine 15 cosine 15 and compare that with the double angle formula for sine. So compare that with the double angle formula for sine. Sine 2 theta equals, see how they're so similar, right? I mean, this thing right here is just the same as this, where theta is 15 degrees, right? So sort of reading this identity backwards, like in this direction, tells you that this expression must be just equal to sine of twice theta. And what is theta? Well, it's 15, so sine of 2 times 15, which is just sine of 30, right? Which actually we know what sine of 30 is. It's a half. So that's the answer. F, very similar. You should hopefully notice that 1 minus 2 sine squared pi over 8 looks a lot like this, right? 1 minus 2 sine squared theta looks just like the cosine double angle identity, except theta is what? Well, it's pi over 8, right? So, reading this identity sort of backwards, like going from here to here, you can see that this expression is just cosine of 2 theta. And what was theta? Theta was pi over 8. So cosine 2 times pi over 8. Well, that's cosine of pi over 4, isn't it? Which, of course, we know is root 2 over 2. So that's how that works. G, very similar. You look at this expression, you're like, that looks a lot like something, right? It looks a lot like the tangent double angle formula, 2 tan theta over 1 minus tan squared theta. So we can see that this thing, so what is theta, though? Theta, of course, is 7 pi over 12. So reading this identity sort of backwards, you can say, oh, this thing is really just tangent of 2 theta. And what is theta? Theta is 7 pi over 12, which is going to be tangent of 7 pi over 6, which is going to be, let's see, where we found the tangent of 30 degrees earlier, right? 30 degrees and pi over 6 are the same angle. And we said the tangent of 30 degrees was root 3 over 3. So this is like pi over 6 right here, right? This is pi over 6. 7 pi over 6 is right here. It's just past pi. So the tangent's positive in this quadrant, right? Because both the x and the y quadrants are, both the x and the y coordinates are negative. So yeah, so the tangent of 7 pi over 6 is actually the same as the tangent of pi over 6. It's just root 3 over 3. Okay. Cool. Okay, well, like I said, like I say here, you should review your derivations of some of the formulas that we found, right? Like, remember how we found the double angle formulas, right? You'd write, like, sine 2 theta. How did we derive that one? We'd say, oh, sine 2 theta can be written as sine of theta plus theta, right? And then you applied the sine angle sum formula to this thing, and that's how you get the formula. So review that derivation. Try to do it again on your own. Same thing with cosine double angle and tangent double angle. See if you can review those derivations. Okie dokie.